Right. Can everyone see my screen?
Yep.
Just in the nick of time. Welcome, Aaron. So today we're going to talk about design for manufacture, design for assembly, and DFX, where X is a variable, meaning, design for any other particular criteria that you're trying to optimize around. This is a huge topic, so it's pretty challenging to cover what everybody needs. I'm going to try to leave as much time as we can at the end to really discuss or dig in on things. I think this is a particularly valuable topic to have a discussion amongst people with different backgrounds and experiences. All right. For those of you who don't know me, my name is Matt Verlinich. I work for InnovationWorks, managing our manufacturing programs. Also on the hardware team, we have Jesse Mazzoni, who manages Alpha Lab Gear, and Mike Formica, who is the director of all of our hardware initiatives. This program is sponsored by NextCore, our program partner based out of Rochester, New York. They are a similar organization to both InnovationWorks and Catalyst Connection, trying to serve the Finger Lakes region of New York by connecting startups and manufacturers and helping both types of businesses. They developed the original curriculum, and we've been working with them to iterate and improve on it. So we'd really appreciate any feedback you can provide us. The program is funded by NIST. The NIST MEP network stands for Manufacturing Extension Partnership. Catalyst Connection is our local manufacturing extension partner organization for Southwestern Pennsylvania, and their mission is to serve and help manufacturers in this area improve their businesses and grow. Also sponsored by NISTAR, the New York's State Science, Technology, and Innovation Department, which is another primary funder of NextCore. So in addition to us and NextCore, the content for this program has been contributed to by the Rochester Institute of Technology. They'll also be doing the full MRL assessments for those of you who received a grant. And then we also have their partner Infuse Hub, which is a sort of statewide MEP for New York, and Catalyst Connection, our local MEP partner. So this is the 5th session in an 8-week curriculum. In the first week, we talked about product development and specification documents, aka your PRD, product requirements document. Then in the second, we talked about bill of materials and bill of process. Third, we talked about cost and risk management. And then the fourth, we did an introduction and overview to quality, both production and prototyping, general quality. Today, we'll be talking about DFM. So first, we'll talk about common manufacturing processes, because that's where everything really starts, and some considerations for selecting a manufacturing process. Then we'll go into an overview of some DFM principles, DFA principles, and then a few selections of other variables that you might want to optimize your design for. At the end of it, I think it'd be beneficial if you tried to think of one of these principles that could apply to your product or prototype and how you might begin to sort of apply it to your design. And chapter 10 in the book, Product Realization, Going from 1 to 1 million, or go to a million, is what covers this topic. So just a brief overview. Costed bill of materials and bill of process is a really, really useful, almost essential tool for doing a DFA analysis and a DFM analysis without identifying sort of what your unit economics are for each component and then how that sorts out as a percentage of your total unit cost. It's really difficult to prioritize and identify what your budget is for, spending money to optimize a design. It's very straightforward and when you think of it in terms of a BOM, because that's a physical part. But whenever you're talking about design for assembly principles, that becomes much more of a murky area, which many people don't consider because they don't actually have a costed BOM where you have an actual, how long does every step in this assembly process take? Also, many people who rely on contract manufacturers, it becomes an even more difficult process to manage how an outsourced contractor assembles your product for you. So we'll talk about some of the ways in which that might impact you, or you might be able to still work through that. So logistics update. For those of you who missed last week, I did finally get the landing page up on scalableinnovation.org. So all of the recordings, if you want to go back and rewatch anything, are going to be posted on there, as well as links to the sort of individual Eventbrites. However, this particular Google Meet ID will be the same one every time. If you want to put a recurring calendar invite on, we're not doing it next week though, because of Thanksgiving. I would really appreciate it if you guys could fill out this survey. If you happen to watch any of these recordings afterwards, or if you missed any presentation live and actually went back and watched one, it'd be really useful for me to know who went and watched them, and if that was actually a valuable effort for recording and sharing these. Same thing with the feedback surveys. If you have any input or feedback or thoughts on what should be covered or emphasized more in any of these presentations, I put a survey for each one in the overall curriculum outline, which is linked on the Scalable website as well. And for those of you who received one of the Next Core grants, in order to get that process started, we'll need you to make sure you fill out your full MRL assessment and a project roadmap for how you intend to use those funds, and put some time on my calendar to go through that so we can kick you off to the next step. So now that house cleaning is up, or housekeeping, let's talk about manufacturing processes. So we'll save the group discussion for the end, or if something jumps out at you in the middle of this, feel free to interrupt. But I actually love this book. I highly recommend it. If you are a maker nerd like me, or if you're not sure that you found the right manufacturing method for any of your parts, Manufacturing Processes for Design Professionals by Rob Thomas is a beautifully illustrated book, and it's broken down very much how I think about making things. It has these 5 major sections: one for forming, which you could think of as like casting or forging or hammering out a bulk part; cutting, which would be a subtractive process, machining a bulk part into a final shape; joining, which is mechanical, thermal ways of joining, so welding or bolting, and PEM studs, anything like that. It sort of covers those things. Finishing is your final steps, the either additive, like painting, powder coating, or subtractive, like sandblasting or grinding and finishing. Then they also talk about printing and, like, pad printing and post-processing elements like that on there. And then the 5th section is a general overview of a whole host of materials and where they sort of shine and why you would want to consider using them. It's great because then in the forming section, it is broken down in a subcategory by each one of those general classes of materials, like forming processes that apply to plastic and rubber, or metal and so forth. You can see in this, this is an overview of, like, each one of the processes gets this page where it does an overview of the sort of cost, the speed, quality, relative cost, like low to mid cost on tooling, low to mid production volume, etc. Shows you what type of shapes it can make using this process, if it's like a hollow shape or a symmetrical shape, folded, flat, etc. A brief outline of how the process works, and then it also does a case study for an exact product like this and why it uses that method of manufacture. Incredible book. For the digital native and free resource, we also have the Build for Scale curriculum, which we pulled some slides out here, but I also linked to those presentations, which you can go through as well. This is just a different philosophy on thinking about how things are made. You start with a raw material. This would be a commodity. It has primary processes which shape things. So this is very akin to the forming section of it. They use forming in terms of, forging or press work, but also separate out molding versus casting, powdered metal, specialty like composite layups, additive manufacturing. Secondary processes they talk about both the finishing and surface treatments in this category, as well as the joining processes like, they separate joining processes down into like a sort of tertiary final assembly process, but they consider the subtractive methods secondary processes in the build for scale methodology. So here is an example of the two sections, modules 3C and 3D. They're also linked in the curriculum overview, but let me see if I can quickly navigate back to where I had those pulled up. Yeah, so this is an example of the full content of what's in there. Breaks down primary processes, casting, what are some common applications, injection molding, O-rings and plastic bottles, has some pictures in here. Secondary processes. It's a great overview of things to think about and maybe consider where and how you might want to make stuff. And then the 3D has some more detail about how these things you should consider each method of manufacture for specific sort of design for manufacture, design for assembly principles like this. Can your parts be nested? An important consideration for many forming processes like sheet metal. Additional details about tolerances and forming and things like that. Also a great resource, but some select pieces of those presentations to consider in your manufacturing methods. Consider what features are part of your part geometry. Is it flat surface? Does it have cavities? Thin, hollow? Is it curved? And then this is a sort of subset of specific processes which you might want to look into for how that type of geometry could be made. So maybe you only ever considered that your part could be machined, but you happen to know that it's like a thin part or a hollow part. So you can look up these terms to try to find other manufacturers or manufacturing methods that might be able to produce that in a more optimal unit cost at the volumes that you're working at. There's also charts which will talk about different attributes. So what kind of surface finish can turning versus milling achieve? What is the relative labor cost, equipment cost, and tooling cost for these different types of processes? And then production rate per hour is another interesting one. Now, I haven't fully vetted this chart. Some of them I think may be a little bit off based on just my experience, but it's a really great general tool to look through. So this is all machining processes, and then it also goes through shaping and forging processes. What's up, Mike?
What is EOQ again?
I think this is, I'm not sure actually. End of life order quantity, maybe? No, I'm not sure. But these are pulled directly from the build for scale template or slides. So if you go into that presentation, it might actually cite what specifically it's talking about. I'm trying to think of what that would stand for. Economic order quantity. Thank you, Laura.
No problem.
Broken down in addition to machining, forging, casting, additive manufacturing. Now, I will say one of the challenges with the build for scale curriculum is that it's not live. It's not livingly updated, so it doesn't have all of the most up-to-date methods of manufacture in there. And then these figures are also obviously rough numbers and relatively static. So there are other methods of additive manufacturing, which I would definitely say can have higher deposition rates than this and different specs on what type of parts they can produce. So some factors to consider, as in addition to everything that we just talked about: material selection, final shape and appearance, your desired tolerance and surface finish, design requirements, such as, how durable it needs to be, how heavy it needs to be, what is your budget for tooling costs, and what is the ultimate market price. What are your margins on this? Do you have a specific price that you need to hit, or can you afford to overbuild it? And then safety and environmental concerns, which is a DFX principle that we'll talk about a bit more later. So here's a whole host of questions to consider whenever you're asking or considering selecting a specific manufacturing process. But what material properties are important? This is something that mechanical and materials engineers are great at. Is it the Young's modulus, the ultimate tensile strength, the stiffness, the toughness? There's a whole variety of different material properties that you might want to consider. What standard processes apply to that particular material? What are your order volumes? And this is something that oftentimes when you go to talk to a manufacturer, they will speak in terms of annual order quantities, but you'll also want to consider batch sizes and how frequently can you order. Are they fitting this into a production schedule that can stop and start within a day, or are they going to want to be planning for weeks or months of production at a time? And those are important criteria when considering this, selecting a particular manufacturing process. I would also say critical to the process selection is the size, shape, and complexity of it. This sort of harkens back to what was shown in that design processes or manufacturing methods for design professionals. Is it a hollow shape? Is it a thin shape? These are critical, but then also on the ultimate assembly and warehousing side of things, how big is this part and how many can be accommodated by a given contract manufacturer at any given time. So if two contract manufacturers have different size facilities, one might not be able to set up a second parallel assembly or manufacturing line for your given part because it's just physical size constraints, limitations. Questions in refining that selection, once you've sort of narrowed it down to a subset of manufacturing processes: how critical is cost to you? How quickly do you need to get these parts? Can you wait for tooling? What is your budget for tooling? And then what kind of secondary processes need to be done in order to finish the part? Is that something that the given contract manufacturer you want to work with is capable of doing in-house, or are they going to sub that out? Depending on communication dynamics, some contract manufacturers will never tell you that they're actually subbing portions of it out, and then that will ultimately frequently result in lead time issues because they're subbing it out and their subcontractor is unreliable. So if lead times are critical to you, it's even more critical that you fully understand the entirety of your supply chain without relying entirely on one CM and taking whatever their word is for it. That also goes for assembly as well. So now, do these capabilities align with what you have internally? This is another thing that oftentimes early stage startups face and ask time and time again. You start out with a small team and you want to just pay somebody to do everything for you, but you don't necessarily even know all of the specs that go into the full process. I really would hazard anybody away from trying to work entirely with a contract manufacturer before you fully understand everything that goes into assembling it yourself. Otherwise, you then become beholden to that contract manufacturer. So building out the understanding of these different processes, at least in a basic level internally, is critical. Then that also allows you to understand what questions to ask your suppliers about their capabilities. Are they subbing something out or are they not? For instance, if you're working with a sheet metal part and it needs to be powder coated and they say that they can deliver it to you powder coated, are they powder coating it in-house or are they sending it out to powder coat? They aren't going to have full transparency into the production schedule of their subcontractor. So they might assume that it takes them normally 2 weeks to get it in and out, but it actually, around a particular time of year, maybe it takes them 8 weeks. Another interesting thing that I've run into a number of times with portfolio companies that we work with is how willing is your manufacturer to learn and to also invest in new materials or new processes. For instance, one local electronics contract manufacturer didn't have ultrasonic welding in-house, but the portfolio company that we were working with needed to ultrasonically weld their casing shut so that it could be an explosion-proof environment. They developed a joint agreement so that the startup and the manufacturer would sort of finance the piece of capital equipment that would allow them to then offer this service to other people, because the startup had no interest in owning and operating an ultrasonic welder, but also didn't want to foot the bill fully for something that ultimately added value more to the manufacturer over the life of the tool. You can negotiate things like that with manufacturers given the right relationship and their willingness and ability to grow or float certain capital equipment expenses like that. So now that we've talked about manufacturing processes, we'll get into the actual design for X principles. Why is this important? I do like this illustration of the shadow that is cast by your design decisions. Ultimately, your product design might be 5% of your hard costs, unit cost that you can account for, but at the end of the day, 70% of the lifetime cost of producing and delivering that product, given the opportunity cost of how things could have potentially been made. That being said, I wouldn't necessarily go overboard in optimizing before you've fully vetted your design. And that's one case where the MRL framework can actually be very useful in assessing how mature is your design, at what point should you really dedicate some serious resources to optimizing. So some general things to consider: the importance of design. It saves you on rework time, minimizes tooling or retooling costs, avoids inventory scrapping costs. This is something also that often is neglected in initial financial forecasts and cash flow models. So it becomes easy to make maybe inappropriate design or supply chain decisions whenever you're not factoring in all of these costs. It ultimately can also result in better quality, which would allow you to sell more products. Intellectual property is another really critical aspect of design and something to consider. Depending on where you're making your product, if maybe one startup that we've worked with will not load any of their software on the product, but they make it in China, because the software is the real critical key differentiator in their product. And so they do all of that in-house after the fact. Some local electronics contract manufacturers that I'm aware of do have subsidiary partnerships overseas to get better unit costs and lower volumes, and they have an existing relationship with a very particular firm, so they'll be more willing to actually load that firmware on there for you if they produce it overseas. But if you went and produced it overseas, very few contract manufacturers in our areas are going to be willing to just load firmware for you on something that's already done. The reason why this is the 5th presentation in this whole series, and we haven't even discussed it until now, is because everything is interconnected in the whole design optimization side. And until you have a good idea of what your specifications are, if they keep changing, it's going to influence what process you should select, and what process you select can influence what materials you are able to use. Your geometry is going to limit what processes and what materials you can use as well, and also your specifications be that everything is interconnected. So we start very deliberately from understanding and defining very clearly what are your specifications that you need to hit, and then focus on the bill of materials and bill of process so that you can actually get those down and organize them and understand what is influenced whenever you do make design changes. So DFX principles, some other alternatives to design for to consider: sustainability, reliability, testing, maintenance, and one that I didn't bold on there is logistics. I would say those are some of the real other huge topics to think about early on, not just ultimately your unit cost, but what is the total lifetime cost of this product in servicing, in quality certification and management, servicing reliability issues, and then shipping. So all of these principles really start to take hold at this MRL level 4 or 5. That's when you have your engineering validation testing prototype. It's your first sort of assembled, looks like, works like prototype. That's whenever you're beginning to sort of identify what specific manufacturing methods are going to take you from where you are right now, proving out this design to scale at either your first pilots or your commercialization stage. So DFM can't begin to occur until you've already selected those processes, but you have to first prove out that your design meets your customer requirements before you can begin considering those things. Also remember that DFM and DFX principles are a continuous process. And that is one thing that I think is challenging with the MRL framework, because it portrays itself as a very linear process. But in reality, sometimes the outcome of any given particular design change or improvement project might be that it sets you back in the MRL level, because you found out that the design needs to be changed and revalidated before you can move forward in the first place. So DFM identifies where the design will not allow manufacturing processes to be used, result in costly processes or long cycle times, and also potentially result in poor quality. So cost, quality, and lead time, those are the three things that dictate all manufacturing decisions. And how do you conduct a DFM review? This is a challenging question, and it depends, again, on your particular product, your particular manufacturing process, and your particular choice of who to work with. Some contract manufacturers are ultimately going to be way better at doing a DFM analysis than you ever would be, because they are going to conduct it for their in-house equipment. They know that equipment better than anybody else, and it's not worth it for you to try to micromanage them, but you will still ultimately have to manage that project to make sure that they are considering all of these different potential variables. It's a delicate balance to strike between making suggestions versus micromanaging. Prior to that, I think that it's extremely valuable to have an internal review of your overall design and make sure that you've actually considered all of the applicable manufacturing methods for your part. Have you really vetted your forecasts to understand what your reasonable expectation is for your order volume? What is your budget for paying professional engineering services or NRE costs from your CM to do an analysis on a part? and also what is your budget for tooling and other NRE type expenses, which can ultimately result in a lower unit cost, but might require more capital upfront. There are a host of online DFM tools and software. I would encourage anybody, if you have any good resources, please share them with me, because I'm trying to compile that into this curriculum so that it will be useful for everybody. But some of the best ones that I've found are through the sort of instant quoting type CMs like Proto Labs, where they do a pretty great job of allowing you to upload a design, particularly for machining, sheet metal fab, and injection molding and 3D printing, and will give you really good feedback on suggestions for your design. That being said, it's not always going to catch everything. And for instance, the part on my product is a large part. It's a thin walled vessel, which I designed so that I could use either thermoforming or pressure forming techniques or injection molding. And Proto Labs, because of their particular dynamic of how they like to process orders very quickly, would only do that with a 3-part mold. So it's, instead of just a straight pull from the center, the top has to separate and then pull from the bottom, which puts the bottom, the floor of tooling costs for a 3-part mold is always going to be higher than the floor of tooling costs for a 2-part mold. So they didn't even offer it as a suggestion because their machines can't do it. That's another reason to make sure that no matter what you're doing, you should always try to get multiple quotes from multiple different sources, because the resident DFM experts at in-house at any CM are going to ultimately be most familiar with the machines that they have at their disposal. So that's the last point on this, is send your part out for quotes and get a solid distribution of quotes so that you can make informed decisions. They're also going to be factored in, that's also going to factor in like real-time, real-world analyses. Like, are there supply chain issues on a particular polymer that you intend to use for your part? Does one CM already have a stockpile of that in-house because they do other parts with that, versus the one that gives you the lowest quote is assuming that they're going to be able to order it and then they suddenly can't. It's one reason to make sure that you actually get real-world quotes when you're ready to place that order. So it's useful to consider also the potential impact of changes down the line once you've sort of selected your manufacturing process. Is your design finalized enough that you know you're not going to have any major changes? Major changes would be things that include, refixturing or the use of a specialty piece of equipment like a 5-axis mill instead of just a 2 or 3-axis mill. And minor changes are things that can be done after you've even already paid for your tooling, like adding radiuses or draft angles or bosses. One thing I will say, it's always easier to add material to a cast part because that involves just subtracting volume from the tool, versus adding volume to the tool requires somebody to go in there and lay down a weld bead and then machine it and then refinish it. It can be done, but it's going to introduce more potential failure modes and quality issues. So even if it doesn't cost you that much, it might cost you on the management side of that. So something to consider. So design for assembly principles. This again is really going to factor in when you reach that MRL 4 or 5. And ultimately what you're trying to do is reduce your labor costs and reduce your cycle time while also improving your quality. Those are the 3 big objectives in any DFA analysis, or DFA project, I should say. Things to consider and how to accomplish that is Does the overall product architecture help or hinder assembly? And does it also restrict specific assembly methods that could be used to potentially reduce the cost? So automation, basically. Can your part be assembled automatically, or does it have to be assembled by hand? This is oftentimes the case with hardwired boards. If you have to solder daughter boards together based on your design, that is going to be a process that almost always is going to be done by hand by a human being, and therefore limits the both production rate and the cost that you can ultimately get down to. The overall architecture issue is something that you can consider by techniques like the poka-yoke assembly method, which is error-proof assembly, basically. If you have parts that cannot go together in the improper configuration, can you assemble the front plate of your product upside down? If so, somebody will likely do it. But if it physically cannot go together, that oftentimes saves you in quality issues as well as assembly time. Standardizing parts is a huge one. If you have 13 different lengths of screws, you're going to have to manage all of the supply chain on all of those different lengths. Is it possible to get them all to the same diameter or the same length? Ecotone actually was just telling me they did a great job of that for the piping in their digester, so that it's all standardized, I think, into 3, 4, 6, and 8 inch lengths of PVC pipe, as opposed to 3.5 here, 4.25 there, 8.5 here. Also, minimizing the overall part count on your bill of materials is another huge opportunity. This is another super critical reason why we emphasize getting your bill of materials and at least a rough bill of process down as soon as possible, because without those tools, you won't necessarily know if you're overcomplicating the design. The average car has about 30,000 parts in it. That is a really complex machine with some of the most advanced supply chain for an everyday product that we actually interact with, short of rocket ships or space probes. And those things are produced all the time. There's a really well developed process and infrastructure for that can be applied to a lot of the products that you guys are working with here. Another technique is designing for top-down assembly. So think about it from this perspective. Every time you have to reorient your product during the assembly process is an opportunity to lose things, misplace things. It's wasted time in the overall assembly process. Can it be designed so that everything goes in from the bottom? So you flip it upside down, you put everything in, all of your connectors are assembled in that series, and then you close it up and it's done. One very specific design principle. This can be done after you've already selected your manufacturing processes that you intend to use, but not necessarily after you've already paid for the tooling to produce them. So one more example of why it's really, really helpful to develop your bill of process ahead of time. If you're looking to learn about this without having to spend the money or a whole lot of time on your own product, a great way of doing that is tearing down or disassembling other people's products, especially comparable ones to yours. And there's even a whole ton of these types of videos online. Fictive does a great job of tearing down different products, and they bring in sometimes the designer of that product originally, sometimes other experts from the field to assess how good of a design was this in the first place. And they talk about a lot of these principles. They just keep coming up where it's like, oh, these two parts do the same function, but they are mirror images. Could they have been made symmetrical so that you can create one mold that has 2 cavities and produce 2 of these same parts with every shot, instead of having to produce one of them with every shot, and then have to manage the extra part numbers and assembly steps to make sure that the right hand and the left hand go on the correct side of the ultimate actuator. There's a whole ton of DFA and DFM principles and stuff like that, which I just love. But another super common DFA principle is carefully consider what fastening method you are intending to use. So ultimately, the best way is to make it a single part, which that involves sort of snap fit connectors. And that has to be designed into the part itself in order to make that possible. Because any other additional step is going to cost you on time, which is money. So material joining, welding is ultimately the best way, but also can be the most expensive because there's a whole range of quality that you can get from just welding or brazing or anything like that. The chemical method of that is glue and or tape. Those are things that, while they can be done and used in products that are designed to last a lifetime, they require a pretty careful analysis and preparation of the part. So I'd highly consider not using glue or tape anywhere if you can avoid it. Permanent mechanical fasteners like rivets are great and can be automated fairly quickly and easily. Temporary ones like nuts and bolts and things like that ultimately allow you for a maximum flexibility, but they are some of the more expensive methods for joining things, and not only just in your actual part costs, but also in managing that supply chain. Threaded inserts and self-tapping screws can be really useful methods and as a good intermediary step. Instead of having to manage a nut and a bolt to assemble something, you can mold in at least a boss into a casing that you can then just run a regular self-tapping screw through. And that's a simpler way, but still more effective or more expensive than a snap. It might be more reliable or robust though, especially in dust-proof or waterproof environments where you need to ensure a certain amount of clamping pressure in order to get a certain waterproof or dustproof rating. Snap fits aren't always going to be an option. So I've alluded to all of these things just in context there, but a summarized list. What are your products best when you're considering a method for fastening your parts together? Consider what your specs are. What type of forces or loads is it going to be under? What are the environmental conditions? Does it need to be waterproof or dustproof? Is it going to be subject to vibrations? Does it need to be like a Faraday cage for electromagnetic interference so as to make electrical contact? Whole host of things there which are going to influence your materials as well. Capital costs. How much does this cost to actually assemble and manage the supply chain for these types of parts? It's also consider what it does to your selection opportunities for the contract manufacturers that you can work with. One of our companies makes a pill package for like pharmaceuticals and like over-the-counter pharmacies to fill your prescription medicine into out of folded paper. Now, there are machines out there that can do extremely complicated packaging and folding operations, but while there is an enormous number of packaging suppliers, there are relatively few that have these very complex machines. So if you design it in such a way that has to utilize one of those machines, you're either limiting yourself to working with one of a small number or designing a custom system to do it yourself in-house. What are the part costs? Is there an opportunity for robotic or automated assembly? If so, do you have to do that, or does somebody else already solve that problem? What are the costs there? And then the need to disassemble is a huge one. You can't glue something shut that might need to be serviced. What are your unit economics on potentially servicing that down the road? Is it cheap enough for you to just throw it away and send them a new one, or bring it back have them send it back, and then you have an in-house team to harvest the valuable components from it to reuse? Important considerations. So another slide from the Build for Scale. Remember that this is also an iterative process. That's a really good point about SKUs. Consider reducing the number of potential SKUs. Stands for stock keeping unit. And so this is like a t-shirt. An Alpha Lab Gear t-shirt's an Alpha Lab Gear t-shirt's an Alpha Lab Gear t-shirt. However, if you're a small, medium, or large, you need to have a different SKU for those different sizes. Do you want to stock 6 different sizes, or do you want to stock 3 different sizes? What does that impact on your ability to sell to different customers? How discerning are they for that? This is really critical in terms of your overall design for assembly and manufacture. Something that people consider as well is anodizing or finishing costs. You can easily switch the color of a part in an injection mold setup or after anodizing it, but it's still going to be a second step in the process. You're going to have to be able to manage how frequently do you order, what's the setup costs to do that, how and where are you going to separate and manage the inventory for each of those different types of components or SKUs. Is it worth it? Does it really improve your saleability to your customer? Does it improve your conversion rate enough to justify the added expense of managing those and the potential quality issues that come from it? This is a case study from the Build for Scale curriculum, which is a really great one. It's just a battery tray. In the I can't remember if this is a Ford Focus or not, but this is a really great example of why it's important or valuable to have a bill of material or bill of process. If you recall back to our bill of process, each one of these stands for a different component and or a different step in the assembly process of this battery tray. The whole purpose of this battery tray is to just hold a battery. Is it really worth it to have all of these different components and steps? Is there a simpler way to go about like solving this problem? Almost certainly. And that is a really critical reason why the automotive industry is notoriously difficult to work into, because with 30,000 different components, you can see here that this single part has at least a dozen just to hold the battery. So is that really all necessary? So when you look at your bill of process, look for opportunities to eliminate non-value added processes, anything that involves multiple touches or multiple handling, opportunities to standardize fasteners, which ultimately reduces your total part count and the number of different unique parts that you have. Again, a reason to make sure that you actually identify every single unique part in your bill of materials with your own unique part number, because you might say, for instance, you have tubing. It's all 1/4-inch tubing. Well, just because it's all 1/4-inch tubing that you buy in a 100-foot reel doesn't mean that you shouldn't have 6 different part numbers for each length. Or in the case of Ecotone, like they should have a separate part number for the 3-inch version, the 4-inch, the 6-inch, and the 8-inch, even though it's all 1.5-inch PVC. That way, when you look at your BOM, you can identify, is there an opportunity to further reduce operations and part count by standardizing it maybe into like 3 and 6 and 8. Personally, I think just for you, Dylan, 4 sounds great to me, but I haven't been inside the reactor, so I'm not sure. It sounds great. Eliminating several parts also saves you on purchasing and having to vet in different suppliers if you have to ultimately add new suppliers to your sort of vendor list to maintain that supply chain, and also reduces the number of inspection steps necessary to maintain your quality compliance and the ultimate operation of your product. So go back and review sort of all of the DFX principles in a second. Remember that every step in the build process is an added cost. I'm not as familiar with this case study that was done by FuseHub, but it is a bike rack, which you can see has all of these different steps in the assembly process and their initial design. You can tell just from looking at this that this is mostly just off-the-shelf bulk components like tube steel and sheet metal and metal rod that have been cut and welded and painted to assemble it. The ultimate goal would be to ultimately get this down into a single cast part, because then you can save all of those steps. I'm not sure how they did it, because I don't think this design is possible, but we'll see. Yeah. So is there any particular DFMA, design for manufacture or assembly principle, that sort of jumped out at you guys? I'm kind of curious. Go ahead, Mike.
Always happy to jump in first. So we've been trying to do a bunch of part reduction, and I think we actually hit one that part reduction has been pretty interesting for us, where we've tried to like unify across a couple different SKUs, and so that one has been particularly interesting, where we can reuse components or concepts across, whether it's our baseball sensor, the one that goes into the ball, or one that goes onto a bat. That has been tricky and challenging, but also a whole lot of fun.
That's cool. That's a good point. That like when you have multiple, like a product family, anything that you discover on one design can then cascade into the other designs if they're similar enough.
Yeah, especially we have similar like shock and impact requirements across them. So
Gotcha. Anyone else want to jump in? Yeah, Jesse.
I think the fastening methods stood out to me for whatever reason. We were talking about fastening the other day a little bit, and I don't know, just all of that, just like all the suggestions you had, I guess, felt really valuable. But we even talked about having a little bit of glue on a piece, and I was like, okay, maybe we can rethink that. So,
yeah, that's not the same thing.
Nice. I got a tour of the Zippo manufacturing facility up in Bradford, Pennsylvania, which is awesome because it's like a totally homegrown, bootstrapped, 100-year-old operation that has everything from like some stuff that's been running since the 30s and all the way up to like a $2 million brand new automated assembly line that just puts the insert into the lighter. They used to braze all of the tops onto the lighter insert, and now that was one of their sort of DFM exercises that I don't know even. I think they probably spent $100,000 on just finding the right glue that they could use. They could be applied into the top of the lighter and then UV cured at the production rate that they needed, that would also have the chemical stability for a lifetime to not be eroded by, the fuel that goes into and is intimately in contact with that. Like that's an instance where it was actually useful to use glue over brazing because it massively improved their production rate and ability to automate. But it's a non-trivial engineering feat to make sure that it can maintain the product requirements. Yeah, that was super cool. But all right, if not, we can jump. Yeah, go ahead, Mike.
That's okay. We'll come back to it.
Cool. Next, we'll talk about some other DFX principles. So design for sustainability is obviously an extremely important one, especially in our current throwaway culture of all of these electronics that just don't get reused. or have non-serviceable lithium-ion batteries that are just included in the case. What is your plan for that? Do you care about it or do you not? That's ultimately a sort of a company value, but that's something that cascades all the way back to your design decisions. And I think about this all the time with like my electric toothbrush. It's a completely sealed system and it's inductively charged. It makes it a lot easier to make that thing waterproof, which is super important for a toothbrush, but also it makes it impossible. Like, it's just dead. There's nothing you can do whenever the battery wears out in it. What type of battery can you use to maximize that lifetime? Can you actually get it up to the infinite, or how many million product cycles that it outlives your customer? What's the total embodied environmental cost of that too? Can you use sustainable materials instead of fossil fuel derived plastics? Can you use bioplastics? A huge element of this is packaging. And this is something, honestly, that I'm super guilty of with my business, because every one of my components is packaged individually in a plastic bag, because especially with silicone stuff, it just is a magnet for dust. If there's any dust gets on it and it's extremely visible, but there are almost definitely other methods of packaging that I could select that would potentially be better and more recyclable than the plastic bags that I use. Could use bioplastic, but it's going to cost me time to do that research effort. It's going to probably cost more money, and then it's going to introduce potentially reliability issues of making sure that it actually does get packaged at all once I disrupt how things have been done. Something to consider, which it's oftentimes easier to make that decision and justification upfront before you enter production than it is to reinvest in that process after you've already established a working process. It's sort of that sunk cost fallacy that human beings are just subject to. It's also interesting because we talked about this a little bit in the cost modeling side of things. One of the reasons oftentimes it's cheaper to work overseas is because they ultimately have less environmental restrictions. And so they are able to do things that have a worse impact on the environment. And then you're also, just by making that choice, adding a higher embodied cost to the transportation of that and how many fossil fuels it takes to get your product to you before you get it to your customer. And it's stuff that oftentimes doesn't show up on the balance sheet, but it's still there. And you do have the power to make those decisions. They can have a positive impact overall. Design for maintenance is a huge one to think about. I kind of alluded to this earlier. How likely is your product to fail? What is the lifetime of the product? Are you evaluating that over time to make sure that it's actually accurate based on your initial assumptions, or are they failing prematurely? Do you have the ability to do accelerated life testing out of the gate to find out what your actual performance lifetime is, or do you have to just put it in the field and find out when it's actually out there? Are there any design decisions that you can make ahead of time that can help you to reduce the cost that you might incur whenever you inevitably find out that it doesn't last as long as you hope it did? This gets back to a lot of the specific DFA principles of, how easy is it to disassemble? If it uses snap fits, do they break off? How well are they designed? Maybe you do switch to using threaded fasteners instead so that you can disassemble and reassemble it. Are there any user serviceable parts? And that's something to consider is, can you or do you want to invest in the technical documentation necessary to create user serviceable parts? Or it's really funny. I think about this in terms of like washing machines. My dad just sent me a text a week ago and was like, "Hey, our dishwasher broke. If I buy this part, will you help me change this?" And he found a video that was like, "Yeah, you can do this. You can switch this out." And I was like, "This is going to take like 2 hours to swap this out." And there is a whole industry of appliance repairmen, which is probably honestly dramatically declined from where it used to be back in the day. Because honestly, things aren't designed to be serviced anymore by people, but could be a key differentiator in your market or for your customer. Something to consider. Design for reliability. This is a huge one, especially in specific industries. I imagine, like for Diamond Kinetics, you don't want to service these things once they're out there. They're going to be used in an irregular environment. The amount of variation on the ball sensor, I can imagine. Like, is this being used in Little League or T-ball? Is it being thrown by a pitching machine or a human? Is it pro level? How much of a range do you want that to have? What's the cycles on it?
Mm-hmm.
Is it
what
going
is
to
the
be
backstop? Is it going to be stopped by a brick wall or ideally a glove? But yeah, there's a lot of variation there.
Yeah. So it's not always possible to design for the worst case scenario and just say, good, we're good all around, no matter what can happen.
We're currently in the over design portion of this. So we're currently over designing for our next generation. Actually, one of our guys is over there testing right now.
Nice.
Yeah.
That's awesome. It's super interesting too with the space industry and aerospace. Those are particular industries where public health and safety is super important, but the more you increase that factor of safety, the heavier those things get, the harder they are to launch, the more expensive they are to launch and to stay up, the longer, the more your fuel costs are over the lifetime of it. You might be able to get a couple extra cycles, but is that worth the additional cost over the lifetime of the product? Design for testing is another huge DFX principle, especially in the electronics world, where you can have like a automated test probe setup created so that you can test a variety of pathways or components all in one go, and it can be automated. But asking your CM, how much does that cost, and is it worth it, before you make those design decisions? Identifying and even laying out your board in such a way that it can all be tested from one side before you settle into that, if it's really important to test that. Identifying which components are super critical to test before you lock in that design. These are things that it can be very esoteric. Maybe you have a really great electrical engineer who spent time working actually in a manufacturing facility that can know what questions to ask, but ultimately they're probably not going to know every type of machine. For instance, some of the electronics contract manufacturers that we have just even in our region do have a solder like flow soldering machine. So they can do what would normally be considered only hand soldered components, so like through hole components, and they can do it on an automated assembly line. If you go to another contract manufacturer that doesn't have one of the 5 of those machines that exist in the US right now, they might say, no, that can't be done. And you're not always going to come across the engineer who knows and keeps up with all the latest developments in capital equipment. So definitely things to consider there. Burn-in time is another one. So especially on mechanical components or electrical components that have high cycling or a strong need for calibration, is there a way that you can set in place a quality control test so that you don't need to actually burn in every unit before you ship it out to a customer? BGA components too, which are sort of electrical components that instead of having all the contact points on the outside, they have them all underneath. If that's critical to your operation and you need that sort of footprint, I think the only way to inspect those is X-ray. And a lot of people will have X-ray assembly or X-ray inspection machines, but most of them are manual or semi-manual processes. Does a CM have a fully automated one if you need those types of inspection rates and volumes? Things to consider. This is a case study that I really like that Fuse Hub did on this garden hose reel. Basically, they came to a point where the cost of resin or the plastic that's used to mold this product rose through the roof, and they had to consider whether or not they wanted to just pull the product from the shelf or redesign it. And so they wanted to see what their opportunity was for taking costs out of it, and if there was any additional benefits that they could get in terms of, you know, durability, ease of installation and assembly, packaging and logistics, by changing the design of this. So basic rules of DFX. Fewer parts make things easier. More product handling leads to more defects. Snap fits are better than screws, which are better than glue and tape. I would agree with that in most cases. Plastic and metal is not completely rigid. Definitely have to account for spring back and built-in stress. Some other ones. Remember that the tool has to get in and out of your part, so fasteners can't be completely captive. Changing material states, anytime you're casting a product going from liquid to solid, there are considerations that need to be factored in for shrinkage, sink, and then also embodied residual stress and sort of the crystallinity of your material. Generally, things don't like sharp corners unless they're machined. You can't really produce it, and they always result in stress concentrators, which make likely points of failure later down the line. Vibration is a serious failure mode to consider, and the best DFM process will fail if the process is not controlled. So going back to that DFM, I don't know why that was just thrown in there, but this was the original design for that garden hose reel. So you can see these sides are like blow molded, so they're hollow and they can't be nested. Everything's screwed together with mechanical fasteners, and basically it was way over engineered. So they weren't able to continue selling this, and they were ultimately going to forfeit their retail shelf space, which is another factor to consider. Is once you go through the effort of building a relationship with a distributor, you don't want to forfeit that shelf space for a product that actually sells. So money to re-engineer, it was definitely going to cost money to re-engineer all of this stuff, and they had to figure out if they could actually do it. So ultimately, the change from this design to this design, these are all flat-shaped parts. There's a lot more empty space in this, while also adding to the aesthetic of the use, or the aesthetic of the overall saleability of this product. Now, those parts also nest within one another, so they can be shipped in much higher quantities when coming from the manufacturer, ultimately reducing a significant number of the costs. There's also some usability angles that made it easier. It snapped together to reduce the number of fasteners, and this handle folded in instead of being attached after the fact. So I can't remember if this has, I think they ultimately reduced the unit cost of that by 40% with those changes. So Summaries and key takeaways. The earlier you think about design for manufacture and assembly, the better. Changes early in the design process are ultimately less expensive than modifying the tooling or just living with a higher unit cost over the lifetime of a product. Make sure you understand the manufacturing process that you select and what its both limitations and opportunities for scale are. And DFM and DFA allow you to think about the ultimate downstream costs of your parts. So when in doubt, definitely talk to an expert to help try to identify. And I would add to that by saying talk to multiple and get quotes. Make decisions based on quotes that you get, not based on what you theoretically think you can get of part costs. So again, the homework, try to apply one of these principles to your design. I'd love to hear about it. So feel free to shoot me a message or throw some time on my calendar if you want to go through any of these particular concepts or manufacturing processes. I'm a huge maker nerd myself, and so I read that book actually cover to cover because I love it. So I'm happy to brainstorm if you want to chat about potential alternate methods of making any of your parts. Link to my office hours, so feel free to throw some time on my calendar if you want to discuss in detail, but otherwise we got about 15 minutes left here for questions or discussion. Any thoughts? I'm gonna just go back and throw some of these links in the chat.
I like the sustainability piece. Waste is such a big part of manufacturing at scale. I wonder if you have strategies or ways to keep, especially with like different order quantities, and like if you're going to rotate off of, we've gone from, we're on our next generation, and so we actually did an extended run of our previous generation because we just had so many extra of a particular part. I don't know if there are good strategies for keeping a handle on that sort of thing.
That is a tough one. And actually, RIT, Rochester Institute of Technology, has their Golisano Institute that is specifically focused on sustainability, and they do design for sustainability analysis for companies to identify that type of stuff. I would definitely recommend. Let me know if you're interested. I can connect you with them there. What's up, Mara?
Maybe along the same lines, I wanted to just ask the group if anybody had any great ideas. So our device has two AAA batteries inside. Oops. Let's see. There's a little battery holder inside here. It's holding two batteries in the bottom. And it's a single patient use disposable device. So after it's used, it's thrown away. In the U.S. market, that is, for better or for worse, allowed. You can put alkaline batteries in a hospital biohazard waste stream, and that's accepted. But in the EU, you cannot. So we need to figure out a cost-effective way to kind of redesign. Right now, it's currently held together with 3 screws. Redesign this handle to get the battery out. So I'm playing with the idea of like having a third piece. There's a door down here. I just wondered if anyone had encountered something like this and had good cost-effective ways to get a battery out of a device.
Who designed the enclosure for you?
We worked with a engineering firm, Intermed Labs, to help us.
Because that's the type of thing, like I have a decent experience with CAD, but like I've never designed specifically enclosures, and there are many rules of thumb for doing exactly stuff like that, and I would not necessarily re-engineer it. I would ask people and try to really drill in and get them to be honest with you about, like, have you done this before? Look for portfolio, look for examples in their portfolio too,
Yeah.
to see if you can see anything that they've done before. Because that should be fairly easy to accomplish with like a sliding battery door, just like a pop off.
Yeah, like kids' toys almost. Yeah, like a pull tab. Yeah,
Exactly.
yeah.
Uh,
Interesting.
and
Okay.
also like those screws, like that enclosure could be easily designed to be snap fit together, and then that's going to save you on the assembly time. But I don't know if there's a particular reason, if it has to be like waterproof or anything like that, that they opted to go with the screws instead.
Just putting it out there.
yeah.
I just as an idea, I have a Quip toothbrush. They are designed to be waterproof, and they actually have a screw open on off that allows you to replace a battery. And it does have a similar form factor to kind of what you're working with, albeit a little bit slimmer.
Wow.
So just an idea.
Interesting.
Yeah.
That's great.
That is always a great technique for that too, is finding analogous products that have similar like performance requirements, and then you can also even present that to the professional services firm that you're using and say, can you do something like this?
Mm-hmm. Yeah, I love that suggestion. Cool. Thanks, guys.
Yeah. In terms of the sustainability piece, Mike, as I think about that more, I've thought about this a lot for my business because I do feel a bit guilty about all of the materials and stuff that I use. And I think ultimately what I've come down to is like trying to assess not just what the actual cost of each component is, but its ultimate lifetime cost. So factoring into that sort of bill of materials, how long do I anticipate this being used for? And what is the cost of replacing that? And then in factoring in as well the shipping costs and distance. So
That's interesting.
There are also organizations out there that do focus on manufacturing and material sustainability. My background is in apparel, soft goods, cut and sew. And so, well, the suggestions I have are probably not as applicable to hard plastics. There are larger governing bodies, such as like Blue Sign or the Hague Index that are kind of national, international organizations that tend to have programs similar to this, or other consultants you can reach out to about kind of that life cycle management.
that's a good point too, is like the industry groups. Like, I don't know if maybe on the electronic side, if IEEE would know of any organizations like that, or yeah, I'm gonna look up the guys here and just put that in there.
Can you all still hear me okay?
Yeah.
Had another quick comment to add kind of on the sustainability side. So personally, something that we've really been focusing in on a practical side, and it can actually be a cost saving for manufacturing, is reuse streams. Is like trying to find specific components that you can source from consistent supplies and reusing materials. Because like when we talk about sustainability, yes, we can design our own components to be reused, but if we can actually use other products that would otherwise be wasted as part of our own manufacturing process, I think that's really like the linchpin of being a sustainable manufacturing process. So for example, we use like some large 330-gallon plastic totes, and instead of buying brand new ones, we'll basically get like reused ones that have been used by like a restaurant or somewhere else. And they're actually cheaper. We save about like $300 each by getting one that's not brand new. And similarly on the shipping container side, We could buy like brand new shipping containers or make like a custom housing for our digesters. But instead we get, even if it's a single trip shipping container, so it's still in really good condition, but again, like reusing materials for our construction. And again, like even simplifies and helps us limit our own costs too. So I think that's a way, like scaling, that's something to keep in mind, is like, can you consistently find sources of these reused materials? So I think that's kind of the key to it. But I think in terms of like trying to be and create more sustainable manufacturing processes, like integrating reuse streams into that, I think could be really helpful.
That's a really good point, Dylan. I've seen some like sustainability analyses of shipping containers because of the whole shipping container home movement, where it's like the amount of energy and CO2 that goes into producing a shipping container new is enormous. But then when you factor in the fact that these shipping containers have so many ultimate additional reuses, some of them make hundreds of trips across back and forth, and the alternative would be something that wouldn't last 100 trips. You amortize that sort of environmental cost over the actual lifetime of the product, and you come out with it being worth it. I was thinking of another option too, is like Casper mattresses and all of these like ship directly to your door foam mattress companies. Foamed thermoset plastics are something that is really difficult, if not impossible, to recycle in the traditional sense. But they established recycling partnerships for post-consumer or return stuff that shreds them and then uses that for other products and other form factors. So I think of things in terms of like the embodied energy cost of it. When something is highly designed and formed, it's going to have a lot of energy that went into that. But if you break it down, it might have alternative uses, like a block of foam, which is the shape of a mattress, is like engineered for that purpose. But once it's shredded, it can be used for multiple different other uses that are sort of have less engineering requirements around them. That was another fun fact that I'd learned about from touring a local packaging plant. Considering your customer and whether it's like an actual consumer or a more prosumer user, because post-consumer waste recycling is abysmal and very, very difficult, but industrial use recycling is actually pretty good. So this particular manufacturer makes cardboard packaging, and cardboard packaging is actually pretty environmentally friendly, because if it's pre-consumer recycled, it's like 95% recycled. So all of their offcuts from producing cardboard boxes is actually pulped and reused and made into like recycled packaging. But once it actually goes out to a customer, makes its trip from Amazon to your doorstep, what happens to that cardboard that gets recycled is much less. That's cool. Well, we are at 2:30, so if anybody wants to throw some time on my calendar, I do have some time available right now. Otherwise, thank you all for showing back up. I'll see you in 2 weeks.
Thanks, everyone. Bye.
Thank you. Have a good one.